Greetings and welcome, friends. Mr. Wowdy here. We are in section 8.2, proving triangle similarity, Larry, using the AA similarity theorem. This is the claim. It says if two angles of one triangle are congruent to two angles of another triangle, then the two triangles are similar. So notice these two angles are congruent to those two angles. By third angle theorem, we would have actually already known that those angles also happen to be congruent. But it turns out I know that these triangles are similar to each other. If those triangles are similar to each other, that means that they have a set common ratio between their sides. That AB to DE is going to be the same as BC to EF is going to be the same as AC DF. All right, because those are similar, they'll maintain proportionality in their sides. So we were unable to prove two triangles congruent using only those means, but it turns out we can prove they are similar. So let's jump right down to example 1. It says determine whether the triangles are similar. If they are, write a similarity statement. Explain your reasoning. So what do you guys think, Haley? What do you think about this? I see two 90-degree angles, and 90-degree angles are always congruent to one another. Right angle congruence. But 26 is not the same as 64. Isaiah with the save, alley-oop. And what do you do? Okay. All right. And what would you end up finding this angle to be? What would this angle be? I believe it's going to be 64 degrees. And it's going to be congruent to that one. And this one's going to be congruent to 26. But actually, I wouldn't have even had to go that far. I could have just said 64. I only need two angles. And the triangles are similar. Why? Angle similarity theorem. Well, it's not a postulate. So they are similar. So let's write a similarity statement. Let's say that triangle CDE is similar, not congruent, similar to triangle who now? CD. C is at a point, then it goes to the right angle, so K to G. AGH. By the angle similarity theorem. All right, how about using this to show other facts? Good old triangle similarity. All right, well, let's take a look at it. All right. Show that the two triangles are similar. All right, so check this out. These two angles, definitely congruent. I technically could show that this angle is congruent to itself by reflexive property. And then I could say that little triangle is similar to the big triangle by angle. If I didn't use reflexive property, I actually could have said that these two lines are parallel. Why? Anyone have memories from chapter 3? What types of angles are these two 52s? Corresponding angles. Converse would tell me those lines are parallel, and then I would also have known that these two angles are congruent by corresponding angles postulate. And that could have been enough for angle to prove that. So there's actually a couple different ways I could do that. How about B? Any thoughts? Someone tell me what to do here. All right, vertical angles. Which ones are alternate interior? RSV, which I could label as just angle S because it's the only significant angle at that vertex. And we also could have done this and that one, right? By alternate interior angles theorem. And then by angle, these triangles are similar. Whoa. Similar to one another. Yikes. Oh, guys, how about this one? Example 3. This is a classic. Imagine we went on a field trip today to, like, a flagpole.
Let's do it.
Actually, I'm not going to have SpongeBob write an essay about what not to do at a traffic light. We'll just go on a field trip to one instead. So here we go. It says, a flagpole casts a shadow that is 50 feet long. So that's 50 feet. Let me get a darker color here. So here, this shadow is 50 feet long. All right. A woman standing nearby who is 5 foot 4 inches tall. All right. So she is 5 foot 4 inches. Okay. Casts a shadow that is 40 inches long. And hey, wait, that's kind of like a triangle. And the question is, how tall is the flagpole? Well, let's convert these all to inches or feet. So 5 times 12 is 60. She's 64 inches tall. Is that right? Yeah. And what's 50 feet in inches? All right, 600 inches. Okay. So, yeah, set me up with a proportion. Actually, I called it H, if that's fine. H is to 64 as 600 is to 40. Now, the reason we're assuming this is true is because height is measured perpendicular to the ground. So that's a 90-degree angle. That's a 90-degree angle. And we're assuming that the angle at which the sun's light from, what was it, 93 million miles away from the problem yesterday? All right, something like that. We're assuming that that light roughly hits these two objects parallel to one another. Roughly. Okay? And so we're assuming that these angles are close enough that we'll call them congruent for the sake of estimating the height of a flagpole. Like for a triangle point vertex that's 93.5 million miles away, you could do that, theoretically. Actually, the whole idea of how they try to find the distance of stars to the Earth requires some interesting triangulation as well. But here we go. Yeah, so because I have angle, we're assuming those two things are congruent. Now let's simplify this. I could swipe a 0 right off the bat. I could h over 64 equals 4 divided by 60, or 60 divided by 4 is 15 over 1, or just 15, and then multiply both sides by 64. Right? And I get h is equal to 64 times 15, and I get 960. What's that measured in? Inches in my case. What do I do if I want to convert that to feet? Divide by 12. Actually, let's do this using proportions. So 960 inches multiplied by 1 foot divided by 12 inches. Notice what happens to the units here. There's 1 inch, right? 1 foot for every 12 inches. These inch units cancel each other out. Let's see if I can actually swipe. And I'd be left with feet as the remaining unit. And so 960 divided by 12 is 80 feet. And so now this lady's all like, 80 feet? And that's what she says. Pretty sure. That's what she said. So, all right. Well, thanks for watching, internet friends. That's the lesson for today. Bye.